This will be a quick overview of how a typical American nuclear reactor would operate and some of the accidents that have happened, both man-made and natural, with nuclear reactors in the last 40 years or so. Here you have a schematic diagram of a nuclear reactor. To give you a sense of size, the reactor vessel, that's this thing right here, is probably a little bit more than twice as tall as a classroom. The fuel rods right here would be about twice my height, maybe 4 meters tall. The control rods are right here. These are actually control rod assemblies, clusters of rods made out of cadmium and boron to absorb neutrons. Notice that they are gravity fed, which means when they are lifted up, they are held in place by an electromagnet, and if for whatever reason the electricity is lost, the electromagnet, of course, then doesn't exist anymore, and these control rods would fall down into the middle of the fuel rods, which contain the pellets of uranium 235, 5%, the rest uranium-238, or plutonium-239, and absorb the neutrons to shut down the chain reaction. Now, some other things that you should notice is that we have 3 loops. The first loop is pictured right here. You can see that the water is going to be going clockwise in this loop. The water is going to enter the reactor vessel, and because of the energy being produced by nuclear fission, because you have a critical mass of uranium in the fuel rods, this heat is going to be carried away to a heat exchanger. But it's all under pressure. All this water is under pressure, so it never turns into a gas. And of course, the plumbing, when you have water under pressure, makes a significant engineering challenge. But then again, having steam under pressure or steam in plumbing also is a challenge. But this very hot water enters a heat exchanger. This device is a heat exchanger. Remember good old Q equals MC delta T. And we want to have the greatest change in temperature that we can get. And we want to pump an awful lot of water through to get a huge mass carrying this heat away. And this is a simplified picture of this heat exchanger called a steam generator. But all the heat from this hot water, and there would be many, many pipes here, intersecting the pipes of the second loop, this is where the water turns into steam, and the pink color represents the steam. This then is the second loop. And notice that the water in the first loop never comes in contact with the water in the second loop. The water in the first loop loses a lot of its heat and comes back at not quite the same temperature. Here's a pump that keeps the water circulating for 40 or 50 years even in this first loop. This is the power loop. Now, the second loop is where the electrical energy is actually generated. When the water turns to steam, it operates or pushes past a turbine, which over here rotates coils of wire in a magnetic field to generate electricity. And it's immediately converted into high voltage, low current to reduce the losses. And that's how it's sent long distances to local areas. Meanwhile, we have a third loop here. Here's the third loop. Here's the second loop. Here's the first loop. In the third loop, we bring in water from the environment, and this is going to be colder water, probably the temperature of whatever outside might happen to be. And that enables the water in the second loop, which is already cooling down because it's lost its energy to run the turbines. We cool it down even further, again trying to maximize Q equals mc delta T, the amount of heat we're carrying away. And then this water can go to a number of places. For example, it can go to a cooling tower where evaporation cools it down, and then the remaining water that doesn't evaporate can be returned to the environment or recycled. It might go to a holding pond. In any case, it's got to be returned to the environment barely above the same temperature that it came in. So you can see a lot of safety features built into the kinds of pressurized water reactors, are called PWRs, that generates most of the nuclear energy, about 19 to 20% of the electrical energy in the United States from these pressurized water reactors. Now, we've had some major issues. The first one occurred back in 1979. And this is a picture of 3 Mile Island. Guess how long the island is? It's near Harrisburg, Pennsylvania. You've got a number of rivers that begin to meet here. The Susquehanna, the Monongahela, and Allegheny. And you'll notice you've got 2 nuclear reactors. Right here is one nuclear reactor. Right there is another nuclear reactor. They are inside those containment buildings. Those containment buildings are massive structures made out of concrete, reinforced steel, and they're supposed to be able to withstand earthquakes and direct hits by some kamikaze pilot in the 727 jet. These are the containment buildings that Russia's nuclear reactors do not have. We'll see that in a minute. And so the electrical energy from this reactor right here, the water that cools it is going to those cooling ponds. This nuclear reactor over here uses not cooling ponds, cooling towers, these cooling towers here. You'll notice that the ones on the left are still operating because you got water vapor. Regular old ordinary water vapor. The ones over here are not operating because this is the reactor that had a partial meltdown due to a combination of things, a stuck valve, if I recall, an overreaction on the part of the operators who inadvertently cut off the cooling water, and as a result, a lot of that nuclear material melted down, not there, melted down at the bottom, and this is the kind of material that eventually was shipped out to Idaho for analysis. So that was 3 Mile Island. Nobody was killed, and the instances of cancers and miscarriages and birth defects actually went down because people living in the surrounding countryside, when they heard about this, almost immediately they went to the doctor more. Now, in 1986, notice that we just celebrated the anniversary a couple days ago from when I'm speaking right now. There are no containment buildings. Instead of control rods made out of cadmium and boron, they use graphite. And of course, graphite, being carbon, can be combustible. And they were doing some tests periodically in Chernobyl, north of Kiev, in Ukraine, trying to work out some inherent problems with their design, which meant that there was a minute of danger where if water were cut off for whatever reason, like an electrical outage, it was real iffy if they were going to be able to keep that water circulating. They assumed that the momentum, if you will, of the water going through the pipes would be able to carry the heat away before so much heat would cause the thing to melt and produce radioactive steam, which was not going to be contained. It blew the lid off the structure and produced a lot of radioactive steam when it did happen. Well, one of the earlier tests did not solve their problem, so another test was scheduled. And this test had been delayed several hours, so the operators who came on duty were not the operators trained to run the test. So they were poorly trained or undertrained, and they shut off the water, and they did not regain control, obviously. Those operators were killed almost immediately from the huge amount of radiation in the blast. Not a nuclear blast, remind you, but a steam blast. Then the first responders that came in, many of them were killed. So right now, the total number of deaths from this is about 40-some. Now, there will be deaths, or have been deaths since then, from some cancers that statistically, the statistical increase would be explained from this disaster. And of course, Russia did not tell anybody, and it was several weeks before this radiation began drifting across borders to other countries, and we were picking up on it. And then they admitted it. Their first responders were certainly heroes, and many of them really received huge amounts of radiation. Some actually survived. There's a book and a movie just in the last year or so that came out that I hope to read this summer. I think it's called Midnight at Chernobyl, but I'll have to double check. This is the most recent one, not caused by man at all. This is in Japan, Fukushima Daiichi, and there was that huge Indonesian earthquake that created a gigantic tsunami that washed up on this shore and knocked out a number of these reactors. You can see several of the reactors right here. And it also knocked out the electricity to the pumps that were circulating water. And so they had some meltdowns. And so this whole area became contaminated. And when the tidal wave washed back out to sea, it carried a lot of this debris with it. And in the last couple of years, some of this debris has been actually washing up on shore over on California, Washington, Oregon coast, from what I've heard. So Japan is actually scaling back from nuclear. A couple of other countries are doing that as well. But the main point we should make is that, at least in the United States, the number of people killed from the commercial generation of electrical energy from nuclear power, as far as I know, I think is still zero. Whether there have been any mining accidents in getting the uranium or anything else, I don't know. But it's by far and away the safest source of electrical energy that we have. Because from coal, for example, you have large numbers of coal miners who get killed in coal mine accidents, who get black lung disease, and so forth. And of course, both coal and petroleum produce large amounts of carbon dioxide. For people who are concerned about carbon dioxide as a greenhouse gas, and it is, but it's a very, very small contributor compared, for example, to water. But again, the whole key to operating a nuclear reactor safely is this K value. We want to produce about as many neutrons as we need to strike 235 or plutonium-239 nuclei to keep the reaction going. When we drop the control rods in, or our fuel becomes depleted of uranium-235, it goes subcritical, the chain reaction stops. We want to be just barely critical. We don't want to be supercritical. And that's where you produce way too much heat. You can't carry it all away. And the worst thing that happens would be a meltdown. Remember, it's only 5% uranium-235, not 90%, which is needed for a nuclear bomb. So I repeat, a nuclear reactor cannot blow up like a nuclear bomb. There will not be any mushroom clouds.